Okay, I think we should get started, so please come in and take your seats. My name is Peter Shearer. I'm the seismology section president. I'll be president through 2012. Karen Fisher over there is the seismology president-elect. She will be taking over in about a year and a half. Anyway, it's my pleasure to welcome you to this event. This is one of the highlights of the AGU for the seismology section, anyway. I do want to remind you we're having a joint reception with Tectonophysics tonight. This is over in the Marriott, I believe the Golden Gate Salon A, and we're going to be informally honoring our fellows that we have from these sections. And I'm promised that we're not going to have the problem we had last year where you had to pay $9 for a beer. It will be an open bar, I am told. Okay, well, it's my pleasure to begin tonight by presenting the winner of the 2010 K. Aki Young Scientist Award. And this award by the AGU was established by our section in 2008, and it's given every year to an outstanding young seismologist who is within 3 years of receiving her or his PhD. And this year's winner is Germán Prieto. Germán grew up and went to college in Colombia. He came to graduate school in Scripps in 2002, where he worked on analysis of earthquake spectra and source properties in Southern California, in particular on putting rigorous uncertainty bounds on parameter estimation. Got his PhD in 2007, and he did a postdoc at Stanford where he worked on ambient noise methods with Greg Burrows and Jesse Lawrence. He developed a method for analyzing the ambient noise field that preserves the amplitude information, and he was able to make use of that for strong ground motion predictions from noise observations and to perform attenuation tomography using US array data. Since 2008, he's been a professor at the University of the Andes in Bogota, Colombia, and I'm sure we're going to be hearing a lot more from him in the years to come. Tomorrow morning, he's giving a talk on the repeating intermediate depth earthquakes in the Bucaramanga Nest in Colombia. And in addition to all that, he's a fine tennis player. Both Ralph Archuleta and I have been soundly beaten by him over the years. Anyway, please welcome me. Please join me in welcoming Germán Prieto, winner of the 2010 Aki Award. And he has a certificate. Congratulations. Okay, now we turn to the main event tonight. This is the presentation of the Gutenberg lecture, and this year's lecture is going to be given by Michael Bostock of the University of British Columbia. Michael grew up in Quebec. He went to Queen's University, then got a PhD in seismology from Australian National University in 1991. He did a postdoc in Utrecht for 2 years, and then joined the faculty at the University of British Columbia in 1993, where he became a full professor in 2003. He's won a number of awards. I will just mention that he became a fellow of the AGU last year. He's made invaluable contributions to our theory, to the theory of analysis of scattered teleseismic wave fields and our understanding of the structure of the lithosphere and upper mantle and their dynamics, particularly in the vicinity of the Cascadia megathrust. He will be talking tonight about the fate of water in the Cascadia Forearc tremor. Please join me in welcoming Michael Bostock. He gets a certificate as well.
Just want to make sure I've got Okay, well, thank you very much, Peter. I guess if the work I'm going to talk to you about tonight has gained any recognition over the past few years, it's been in large part due to contributions from a number of individuals that I've listed here. In particular, I'd like to identify two outstanding graduate students that I've had the pleasure to work with, Pascal Adet and Stéphane Randonnet, and three exceptionally gifted colleagues that have contributed to the work I have to report to you. In particular, Nick Christensen, Roy Heinemann, and Simon Peacock. In being invited to deliver a named lecture, of course, one feels compelled to draw an association between the nature of the lecture and the individual for whom the lecture is named. And in going over Gutenberg's texts and some of his manuscripts, I find that this is a relatively easy task for me. In particular because it becomes immediately apparent that he was a man with a wealth of scientific talent that he applied to an equally broad range of seismological problems. So I could have really looked at any one of a number of possible associations between the work I'm going to discuss tonight and Gutenberg, but I think perhaps the best one has to do with low velocity zones. Many of you probably appreciate this, but Gutenberg was had a keen recognition for the importance of low velocity zones in deciphering Earth's structure and evolution. He's arguably best known for his very accurate and precise seismological characterization of Earth's outer core. And that, of course, is without argument the largest and most significant low velocity zone on the planet. He's also known for another quantity which is now known as the Gutenberg discontinuity, but I should mention that, of course, the core mantle boundary was for a long time known as the Gutenberg discontinuity. In more recent years, or generations perhaps, that feature, that moniker rather, has been assigned to a low velocity zone in the shallow uppermost mantle. Some of you will know that Gutenberg was a keen champion for the existence of a low velocity channel at shallow depths in the mantle, and the top of that channel often goes by the name of Gutenberg discontinuity nowadays, or G discontinuity for short. In addition to the core and mantle, he also studied low velocity zones in the crust, and I've cited one particular paper where he deals with this topic in some detail. So as you may have inferred from the title of my talk, I want to talk a little bit about low velocity zones, but associated with subduction zones and with water. And in Gutenberg's time, neither of those two topics were issues, of course, in key issues in seismological research. Gutenberg died a few years before, of course, the advent of plate tectonic theory and so on. One does get the sense in reading over the manuscripts, and in particular the later manuscripts in the text physics of the Earth's interior, that had Gutenberg lived a few extra years, he probably would have very much been a part of the plate tectonic revolution. He was fascinated with Wegener's theory of continental drift. He also was speculating or contemplating currents in the mantle, and of course the low velocity channel in the mantle. So he had all the key ingredients, and doubtless had he had a few more years to live, he would have been a main player in that as well. So my talk deals with low velocity zones and subduction zones in water, and I guess in the last decade or so, these have become key issues in earth science. I have a couple of quotes here, one from Bob Stern, where he writes that understanding the operation of subduction zones stands as one of the great challenges facing earth sciences in the 21st century and will require the efforts of a global interdisciplinary team. I think that prediction or plea is being responded to already 1 decade into this century. My co-collaborator, Simon Peacock, writes more specifically that water plays a critical role in subduction zones. In order for subduction to occur, the thrust boundary between the subducting and overriding plates must be relatively weak. water released from the subducting lithosphere increases fluid pressures along the plate interface, which reduce effective stresses and promote slip. And this is very much the nature of the topic that I'm going to discuss tonight. So the data that really drive what I'm going to talk about tonight come from three profiles that have been collected over the past couple of decades along the Cascadia margin. These are three-component broadband experiments, dense experiments. One experiment ran across southern Vancouver Island, what I'll call the Polaris experiment. The CAFE experiment recently completed by Jeff Abers, Ken Krieger, Stefan Rondonnet, and co-workers across Puget Sound, and the CASC 93 experiment envisaged originally by John Nebelek and that traverses southern Oregon. So these are diffraction tomography profiles across these three arrays, and they show two features which I'm going to briefly comment on now, and I'm going to come back in more detail to discuss the finer attributes of these images in due course. But I want to point out that all three profiles show two features. One is, these are diffraction tomography profiles, so we're plotting shear velocity perturbations. One of the features that is common to all of the profiles is a dipping low velocity zone that starts at the coast and dips landward. You can see it on all three profiles. The other feature which I want you to keep note of is the depth axis here. This feature, which I'll describe in more detail shortly, this white line that divides red from blue is the continental moho, and it's evident in particular on Vancouver Island and in Oregon. It's evident on the extreme landward side of the profile, and as you follow it seaward, it disappears. Its expression becomes muddled, and so those are the two features which I want to address in some detail. So here's an outline of the issues that I'm going to address. The first thing I'm going to do is give you a little brief world tour of subduction zone LVZs, as I'll call them. That stands for low velocity zone. Then I'm going to summarize some of the common attributes of these features, and then we'll move on to look at seismic evidence that supports the notion that the Cascadia Forearc mantle is extensively serpentinized. At that point, we'll look at additional evidence that favors a shallow oceanic crust in the subduction zone as being overpressured, that is, very high pore fluid pressures. And at the end of the talk, I'd like to finish up with a few implications. It'll depend, I guess, on how much time I have left. But there are a number of implications which will stem from some of the things that I will present to you. So here are the hot spots we're going to hit. These are all areas where experiments, high resolution broadband experiments have been performed, and where low velocity zones are in evidence. This is not an exhaustive listing of subduction zones. In fact, there are quite a few others for which there is good evidence for dipping low velocity zones. But I'll restrict myself to these ones where we have fairly graphic representations of those features. So I thought I'd start with Cascadia. I've already shown you evidence for low velocity zones in Cascadia, but I think it's important to give a little bit of historical perspective. Many of you know Chuck Langston, and I would love to know whether he's in the audience tonight or not, but he, of course, is famous for quite a number of things, one of which, of course, is his contribution to the development of the so-called receiver function method, which is so extensively applied these days in structural studies. Shortly after he proposed the method, he began applying it, and one of the very first places he applied it was, in fact, Vancouver Island and Western Oregon, precisely at the latitudes where those two profiles I showed you come from. And what he noted was the presence of a distinct low velocity zone, and he proposed that the basal interface of this low velocity zone was the oceanic moho, and went on to make various interpretations concerning that feature. And so from very early days, 1981, we've been aware of dipping low velocity zone beneath the Cascadia margin. 10 years later, John Cassidy and Bob Ellis at UBC went on to look extensively at the low velocity zone beneath southern Vancouver Island, and they noticed that this low velocity zone was also associated with a band of high reflectivity that was imaged as part of the first lithoprobe transect across southern Vancouver Island. And that feature, in fact, was originally associated with the downgoing oceanic crust of the Juan de Fuca plate, but was later reassigned to the overriding plate on the basis of correlations with Benioff seismicity and velocity models. Shortly thereafter, I should also mention work by John Knavlik. It deserves a lot of credit for really what I regard as a visionary experiment, one that set the stage for countless, numerous similar experiments to come in succeeding years. So he suggested that one could arrange three-component broadband seismometers in dense arrays and seek to image structures such as subducting plates in a manner that is of course, commonly done in hydrocarbon exploration, and his proposal turned out to be to very much have merit. You can see here very clear signals associated with the downgoing plate, which it's these very same signals, which of course are processed to produce diffraction tomography images. Okay, so let's proceed now on our world tour. These are results from northeast Japan, and here we see a low velocity zone. This is now a raw receiver function image, so the blue interface is basically the top of the low velocity zone. The red interface is the base of the low velocity zone, and there's a very clear low velocity zone associated with the Pacific plate in northeast Japan. It's visible, lower base is visible to depths perhaps of as deep as 140 kilometers or so. That's the red, what is presumably the oceanic moho as it's been interpreted. The top of the oceanic crust extinguishes earlier, probably by depths of about 80 kilometers or so. So these are results from Kawakatsu and Watada, and I also thought, although most of the images I'll show have to do with scattered teleseismic waves, I just wanted to include this image from a study by Tsuji, Nakajima, and Hasegawa because of the very close resemblance, a high degree of complementarity of the images using two very different techniques with observables that have very different sensitivities. We get highly complementary images which state basically the same thing and tell us that we can have a high degree of confidence in the structures that are being imaged. Here's another image of a low velocity zone, again a diffraction tomography image, again of the Pacific plate, but here we have a rather younger Pacific plate. Northeast Japan, it was something more of the order of 100 million years of age. Here below Alaska, it's something of the order of 50 million years of age. This is, these are data from the Bear experiment by Abers and Christensen, and a result of imaging by Rondonnet, Abers, and Van Kecken. And they observed not only the low velocity zone, which is relatively thick in this particular instance, but also you can see that they plotted seismicity here. They noted that the seismicity, although not so easy to show from this particular diagram, that seismicity tends to cut across the low velocity zone, which provides fodder for thought as to what the mechanism for these deep Benioff events might be. The thickness of the plate they attributed to a thicker than normal downgoing plate at the trench. We have the Yakutat terrain, the Yakutat block, which is known to be a thick oceanic plateau-like piece of real estate that is being subducting, and so they're suggesting that the low velocity zone there is particularly thick because it represents the extension of that thick terrain into the mantle. Here's a result from Greece. Here we again have a thick low-velocity zone, evident to depths of 90 kilometers or so. This is the subducting Ionian plate, but little is known about this particular piece of oceanic plate because of the fact that it's covered by a very thick sequence of sediments, but it's thought to be perhaps as old as 200 million years of age. Results from the MIT group. Here's a profile from the Central Andes. This was one of the earlier profiles, one of the very first documentations of low-velocity zones and subduction zones. This is associated with the Nazca plate, 50 million years of age, and it's not quite perhaps so easy to see in this image, but this is the lower boundary, this positive excursion, variable area pulse, and then the lighter pulse above it is the top of the low velocity zone. And again, you see a very good correspondence between the low velocity zone and Wadati-Benioff seismicity. And as in Alaska, it sort of terminates close to where the low velocity zone is no longer evident. Central Mexico, very interesting because here we have a low velocity zone here associated with the subducting Cocos plate. The blue is the top, the red is the bottom. And here the plate is dipping at a shallow angle of 15 degrees or so to depths of maybe 45 kilometers, whereupon we have a long segment, almost 200 kilometers of flat subduction, so that even in the rather aberrant situation of flat subduction, shallow subduction, this low velocity zone is present. And then off the end of the image here, this is from the Caltech group, there's a very steep change in the dip, and from both tomography and receiver functions, there's evidence for this feature bending over at a dip of something like 70 degrees or so. I'm going to finish off with Southwest Japan. Southwest Japan is often considered as an analog for Nankai because they're both young and warm subduction zones. The Philippine Sea Plate along the Nankai Trough is something of the order of 15 million years of age on average, I suppose. Cascadia is on average something of the order of 10 million years of age, so there is a slight difference in their thermal profiles. One thing that is particularly interesting about this particular profile, which is the work of Kato et al., which was featured yesterday in a session, is that unlike Cascadia, so you see that you see the low velocity zone very nicely, and of course different styles of seismicity occurring at different locations relative to the low velocity zone, including the low frequency earthquakes and tremor, which are these yellow stars here. But one interesting result, which I think by the end of the talk hopefully you will recognize, is the appearance of the moho right to the wedge corner here, and that is a very significant difference from Cascadia, which no doubt has significant implications as to the structure and evolution of the two plates. So let me wrap up the observations of low velocity zones at the global scale with the following points. I think low velocity zones are observed in virtually all subduction zones where there is sufficient density of instrumentation to detect them. The typical thickness varies from anywhere between 4 and about 15 kilometers or so, which in some cases can be explained by the nature of the material entering the trench. Generally, the low velocity zones have trajectories that roughly parallel the seismicity, although if one looks carefully, one will often find that there is seismicity below the low velocity zone, within the low velocity zone, or cross-cutting it, as I've already mentioned it. So there are very interesting relationships which tell us something about the nature of intermediate depth seismicity. The depth extent of the low velocity zone varies with plate thermal history in general, where colder subduction zones show the low velocity zone to greater depths than warmer subduction zones. The upper boundary tends to vanish where there is sufficient resolution. It's often the case that the upper boundary tends to vanish before the lower boundary. And in the vast majority of studies, the low velocity zone is identified with subducting oceanic crust of the subducting plate. So I want to move back to Cascadia now, and we're going to focus on the image across central Oregon. These are the raw features. As I mentioned to you, we're plotting shear velocity perturbations, and due to the nature of both the theory that underlies this work and the waveforms themselves, the image we recover is really a band-limited version of reality. So as I mentioned at the outset, this feature, this white line that separates red low-velocity perturbation from high velocity blue perturbation, that is considered, that is the continental moho. Okay, so rather than seeing a full red block of crust here, we're just really seeing a band-passed version of a heaviside function. As I mentioned, this continental moho is evident at a depth of about 37 kilometers, and it can be traced to the center of the profile, whereupon its signature is lost, and it's not clear what happens beyond. At the at the other end, at the seaward edge, we see the dipping signature of the low velocity zone, which I've already referred to. The base of that low velocity zone is interpreted to be the oceanic moho, and you can see that the oceanic moho is evident from the coast right the way perhaps to depths of 80 or 90 kilometers or so. It loses a lot of its oomph, if you like, its strength by about 45 kilometers, and it's not really clear what's going on at shallower levels. The layer is dipping regularly, and at first when we saw this, it wasn't clear what we were seeing. We thought perhaps there was evidence for initiation of shallow subduction, but I think, as I hope to convince you of, we've assembled a still more compelling interpretation when we consider both the thermal regime of the subduction system and some petrological constraints. So this is a model of the thermal regime for Cascadia developed by Aaron McMahon, who's a former student of Simon Peacock's then at Arizona State University. The warmer colors, of course, represent warmer temperatures. The blues represent cold temperatures. The major structural elements here are the continental moho, this flat line. The dipping layer is the subducting oceanic crust. The light dark lines here are isotherms, and there are a couple of things, I guess, that I want you to take from this figure. First off, of course, we have a plate that has been residing at the surface for 10 million years. It subducts, and of course, it encounters warmer material, and it acts as a heat sink. First of all, it tends to heat up, and of course, it tends to heat up from top to bottom. So you can see the isotherms gently cross-cut the structural boundaries. So gradually the plate is warming up, and in particular the oceanic crust is warming up first and fastest. The other feature I want you to recognize is that in the Forearc mantle region, this portion of the Forearc mantle wedge, you see the isotherms dip down into the wedge. In fact, we've got temperatures below 600 degrees in this wedge region, and both of those observations are what we want to look at now. So we're going to focus on the subducting oceanic crust. This is a somewhat older figure now, but I think it's still reasonably accurate. These are the major metamorphic facies for metabasalt plotted as a function of pressure and temperature. The major facies boundaries are shown in gray. This is from modified from a paper by Hacker back in 1996. And most subduction zones, the oceanic crust would traverse a trajectory which would broadly take them through a fairly steep path through blue schist facies into eclogite somewhere in this vicinity. But because Cascadia is warm, it follows the oceanic crust, the top of the plate, follows a rather more shallow trajectory, which takes it through the lower grade assemblages. And it intersects the eclogite facies boundary at about 1.4 gigapascals, or something of the order of 45 kilometers depth. Now, associated with each of the facies labels are two numbers. One number represents the density of the assemblage, and the other represents the normative, the lower number represents the normative water content. And you can see two things happening. First, as the oceanic crust undergoes higher temperatures and pressures, you see that as it traverses the various facies boundaries, it's losing water. So we're going from 5.2% water, 3.5, 1.2 to nominally anhydrous eclogite. So there's a big last burp basically occurring at depths of about 45 kilometers or so. You'll also notice that the densities are steadily increasing, as of course you would expect, as the minerals undergo phase transitions to denser assemblages. And in eclogite in particular, as many of you know, is comparable in density to peridotite. And in fact, as many are aware, elasticity tends to track density. So eclogite exhibits seismic velocities which are very close to, if not indistinguishable from, peridotite. Okay, so we know something about what is likely to be happening to the oceanic crust now. We also know that we're releasing water and that there is a last major burp, if you like, of water occurring at a depth of predicted to be around 45 kilometers or so, which is shallow mantle wedge type depths. And one can ask the question as to what happens when one exposes peridotite to water. And this is a diagram which tells us something to that end. This is from a paper by Simon Peacock and Roy Heinemann, where they plot the stable mineral assemblages in a hydrated mantle as a function of temperature and composition, normalized silica content in this case. And the green bar represents the range of commonly considered mantle compositions. And as you recall, we have temperatures in the Forearc mantle wedge which lie below 600 degrees. And at those temperatures, antigerite becomes a stable phase. And antigerite is a highly aberrant mineral. It incorporates a lot of water, something on the order of 10% water into its structure, and as a consequence has somewhat aberrant physical properties. So this is the first of a number of diagrams that will appeal to the works of Nick Christensen. This plots compressional wave velocity versus Poisson's ratio for Hartsbergite, which of course is one form of peridotite, and antigerite, which is this stable serpentine mineral, the stable mineral, serpentine mineral in hydrated mantle at temperatures below 600 degrees C. And you can see that there is a significant drop in P velocity of over 1 kilometer per second, and an increase in Poisson's ratio from about I can't read it, 0.25 perhaps to 0.27, which indicates that the drop in S velocity is still larger than that in P velocity. So we expect to see manifestations of this in the seismic images. So here's the punchline as far as our examination of the vanishing moho and the serpentinization of the Forearc mantle wedge. So you have the thermal diagram on the left and the interpreted seismic diagram on the right. First off, as I've said, we were interpreting the low velocity zone as subducting oceanic crust. Okay, as it plunges to greater depths, it encounters higher temperatures and pressures, which, as you will recall, results in eclogitization predicted to occur at depths of somewhere on the order of 45 kilometers or so. This eclogitization liberates water into the cool mantle wedge, and as I've shown to you from a range of petrological data, the stable mineral assemblage in the wedge, in the hydrated wedge, is antigerite, and velocities are reduced. There probably is some free water also present in the Forearc mantle wedge, and as a consequence, we believe that the crust mantle boundary is actually continuous from the landward edge of the profile straight to the wedge corner. But its seismic contrast, the continental moho, if you like, disappears as a result of the fact that we encounter increasing degrees of serpentinization, increasing degrees of antigerite that basically erase this contrast. And in fact, we believe that the presence of antigerite and the percentage of antigerite and perhaps free water as well is so great, in fact, that the crust mantle boundary actually reverses its seismic polarity, such that we have a high velocity crustal material actually juxtaposed against low velocity mantle material. Okay. So there are a number of pieces of evidence which stand in support of this interpretation. I have two pieces here. This is work from Tom Broker and his colleagues where they compiled data from active source profiles across the Cascadia margin. These are refraction profiles. And what he noted was that the so-called PMP phase, which is the P reflection from the moho of the subducting plate, was conspicuously absent along the forearc, and in particular in precisely those areas where we expect that the subducting plate is entering the mantle. So this evidence again suggests that there is an absent moho all the way along the Cascadia Forearc, suggesting that the serpentinization process is in fact a margin-wide feature. Additional support comes from Tom's USGS colleague, Rick Blakely, and his co-authors, who looked at potential field data along the margin. And what you see here are plots of magnetization and gravity anomaly. And if you look carefully, you'll see the horizontal bars here, which represent the forearc region immediately above the corner of the mantle wedge. And they noted that this region is characterized by high magnetization and low gravity anomaly. And these, this coincidence of observation is kind of rare. Witness, for example, ore deposits, usually you associate low density features with high density features with high magnetization. In this particular case, it's an opposite correlation, and antigerite provides a way of explaining that, because antigerite is low density, and yet at the same time it takes magnetite readily into its structure, and so we can have at once a low gravity signature and a high magnetization signature. So there is one complication which we haven't attended to, and that concerns the next part of my talk, that which I referred to as overpressuring of the subducting oceanic crust. And the problem that we were posed after initially coming up with this serpentinization story had to do with the fact that at shallow levels we have this well-defined low velocity zone, but if one looks carefully at the makeup of the overriding crust in this region, it's not obvious as to why this feature should appear as a low velocity zone. So the base of the feature, the oceanic moho, that's clear. We have the juxtaposition of basalt, metabasalt with peridotite material, presumably. The overriding plate, however, is known to be composed of a succession of accreted island arc terrains, which are likely to be dominated by mafic lithologies. And so the question arises as to why the plate boundary, which separates mafic oceanic crust from what is dominantly mafic accreted terrain, should represent such a strong seismic boundary. And this is what motivates really the next section of my talk. Why is there such a large S-velocity contrast existing at shallow levels along the plate boundary? So for this, we're going to look closely at the Polaris profile, the one that crosses southern Vancouver Island. I have here so-called receiver functions plotted for station PGC, which is, some of you I know have been there, that sits on the Saanich Peninsula, very lovely part of our country. These receiver functions are probably ordered in slowness or some meaningful quantity, but I guess the point I want you to note is that there are several coherent arrivals that are present. These early arrivals are so-called direct conversions from the top and the bottom of the low velocity zone. The blue is from the top, the red is from the bottom. So these are direct conversions. The next sequence of arrivals that come in at later times, between 10 and 20 seconds, represent free surface reverberations, reflections off the freed surface, which are then subsequently reflected from the top, blue line here, and bottom of the low velocity zone. And there's another set which are opposite polarity, red on blue. So we have three sets of arrivals which really interact with the top and bottom of the low velocity zone. So it turns out that if one can measure the delay times accurately between the top and bottom arrivals, the blue and red here, and the blue and red here, and the red and blue from the last scattering interaction, that those differential times can be used to very accurately characterize the interval properties of the low velocity zone, independent of the material above it. And so, in particular, we can constrain accurately the interval Poisson's ratio, or equivalently from which can be derived the PVS ratio, and thickness. So let's look at those results. So these are results for the entire profile from the west coast of Vancouver Island right to the Georgia Strait, and what we found frankly amazed us. We found oceanic crustal Poisson's ratios near 0.4. As I'll show you in a moment, most commonly encountered lithologies exhibit Poisson's ratios in between 0.25, which is a Poisson solid, or 0.3 and 0.3. There's a physical limit of Poisson's ratio of 0.5 for inviscid fluids, and so the oceanic crust here, taking these values at face value, is actually closer to water, has Poisson's ratios closer to water than to most common lithologies. So this is yet another diagram stemming from work by Nick Christensen, plotting VP-VS ratio on one axis. Here are the equivalent Poisson's ratio values on the other axis. They're of course non-linearly related, but you can identify the relevant values there as a function of composition again. As I said, most common lithologies plot in something of a cloud, Poisson's ratios between 0.25 and 0.30. Quartz, of course, is highly anomalous with a very low Poisson's ratio, so quartzites here plot at 0.1. Lizardite stands alone. Lizardite is a lower temperature serpentine mineral, so it's in the same sort of family as antigerite, but not a stable phase at the depths that we're looking at. So it's unlikely to be influencing our results. And yet the teleseismic estimates come in at about 2.35 or 0.338, 0.39. So clearly there has to be something going on that goes beyond lithology to explain the results that we have here. And yet again, we appeal to the lab measurements made by Nick Christensen. These measurements made well over 2 decades ago now. So these are plots of Poisson's ratio for a basalt sample as a function of confining pressure for different levels of differential pressure, where differential pressure is the difference between confining pressure and pore pressure. So let's look at this curve first, the one that sort of decays rapidly and appear almost asymptotically. This is the curve for dry rock. So no fluids in this rock, and as one basically increases the confining pressure, the Poisson's ratio of the sample decreases steadily to levels of below 0.28. I should mention, of course, that the confining pressures here only correspond, the upper limit only corresponds to a few kilometers, so we're only looking at pressures equivalent to depths of say 4 or 5 kilometers at this point. But what you'll notice is that when one begins to increase pore fluid pressures, as exemplified by the differential pressures plotted here, then the curves begin to take off on trajectories which take them to higher Poisson's ratios. And in particular, if you look at this particular curve where pore pressure is kept equal to confining pressure, you'll notice that the Poisson's ratio basically takes a positive trajectory from 0 confining pressure, 0.36 Poisson's ratio, to still higher values. And of course, we've got a long way to extrapolate from 2 kilobars, a few kilometers, to say 200 megapascals or so, to 1 gigapascal. But it's certainly reasonable to expect that as we increase confining pressures, we are going to maintain very high Poisson's ratios if the pore pressures are equal to confining pressures. So we come back to the initial the conundrum that I raised, which was why is it that the shear velocity contrast at the top of the low velocity zone is so large if we're juxtaposing two rock types with similar physical properties? Well, one thing to note first before going any further is that at high pore pressures, not only does the Poisson's ratio increase, or the VP-VS ratio increase, but the seismic velocities, VP and VS, also are reduced by levels of 20 to 30%. And of course, VS experiences a larger reduction than VP. So this provides us with one means of explaining the observation, and that explanation is that the shallow LVZ, the top of the LVZ, can be explained by a plate boundary. It's the top of the LVZ, which separates oceanic crust, where fluids are maintained at pore fluid pressures equal to lithostatic or near lithostatic, from overriding crust, where the pore pressures are simply hydrostatic, so that there's a jump in pressure across the plate boundary. And of course, what that implies is that the plate boundary is impermeable. So let me put the two stories together now in one cartoon: the serpentinization of the Forearc mantle and the overpressuring of oceanic crust. When I refer to overpressuring, of course, I'm referring to the fact to hydrostatic pore pressures. So we have the subducting oceanic crust of the Juan de Fuca plate, okay, that we expect will steadily undergo dehydration reactions as a result of the trajectory that it takes in PT space, as you know, from the petrology predictions. That these metamorphic reactions are indeed predicted to produce fluids at lithostatic pressures, and that these high pore fluid pressures are maintained via an impermeable plate boundary over underneath much of Vancouver Island, and that as one approaches the wedge corner, one of course reaches depths where eclogite now becomes the stable phase in metabasalt, and the eclogite reaction has accompanying with it a volume decrease of order 10%, and we can expect that large volume decrease to enable fracturing to occur and breaking of the impermeable boundary at the top of the plate, and allowing fluids to flux into the Forearc mantle wedge, whereupon that wedge becomes serpentinized. The transformation to antigerite, I should mention, is also one that involves a large change in volume, something perhaps closer to 20%. It's a volume increase in this case. So it begs interesting questions as to how that occurs, but fracturing is likely to occur, which may enable fluids to permeate well into the wedge region. Okay, I'd like to close off with a number of implications. I'm not sure how many I'll get through, but let me mention a number of them. I'll first review some constraints that our results place on physical properties, permeability and porosity in particular, of the plate boundary and of the downgoing oceanic crust. I'll point out some of the interesting correspondences between the occurrence of episodic tremor and slip and the low velocity zone that we interpret to be the subducting oceanic crust. Some interesting conjectures on the evolution of the San Andreas Fault that have been made by others, and possibly the origins of arc magmatism. So constraints on plate boundary permeability, these are a relatively simple calculation, really just involving Darcy's law and reasonable estimates for the fluid budget of the subducting plate and the transition, which is effectively impermeable. I mean, how thick is this impermeable zone associated with the plate boundary? If one plugs in the various numbers, one predicts permeabilities between 10 to the minus 24 and 10 to the minus 21st. Normal basaltic oceanic crust, the published values for basaltic crust on the seafloor ranges between 10 to the minus 21st and 10 to the minus 11th meters squared. And so you can see that we're really at they only overlap at the low permeability end, and the fact that we're sampling the structure with long wavelengths, say 5 to 10 kilometer wavelengths, really emphasizes the fact that these permeabilities are indeed very low. Possible mechanisms for an impermeable boundary include grain size reduction at the plate boundary and a mineral precipitation. Yet another figure that appeals to the results of Nick Christensen. These are now results of VPVS versus porosity. And what Nick has done is he's assembled measurements of VPVS for a range of different crystalline rocks. So he has the most points here for lherzolite and granite. We also have basalt and andesite. These rocks are all similar in the sense that they all have porosity, which is dominated by cracks along grain boundaries. And what he noticed, if you look at he's plotted basically VPVS as a function of porosity for different differential pressures. We have the most points for differential pressure of 5 megapascals, and you notice that there's a nice quadratic fit that we can make to these points. There is abundant evidence that both from the seismology and from other seismic observables, which I'll mention in a moment, that differential pressures are indeed very low on the plate boundary. So we can place constraints using these data on what porosity of the subducting oceanic crust must be, and the constraints we arrive with are between 2.7% and 4%. And in fact, this range is consistent with the range, provides slightly tighter constraints, but consistent with a range originally proposed by Roy Hyman, again more than 2 decades ago, using measurements of conductivity. I think he suggested porosities between 1 and 4%, and here I think we can place still tighter constraints that the porosities have to lie between 2.7 and 4% dependent on the actual differential pressures present at the plate boundary. So another association, I don't have, there's grounds for endless speculation here, but I just want to draw your attention to the very close correspondence between the low velocity zone and tremor locations. So these are tremor locations from Aaron Weck of the UW group up and down the Cascadia margin. And superimposed on that are Pascal's 30 and 40 kilometer contours to the top of the low velocity layer. And there's really a very nice correspondence to where the tremor epicenters are mapped and the 30 and 40 kilometer contours of the low velocity zone. And you'll notice that the tremor is really confined largely to where the plate lies between 25 and 45 kilometers or so in Cascadia. And that 45 kilometers, again, as you'll recall, corresponds to where we believe there is a major break in the seal of the plate boundary. So certainly grounds for speculation that I won't go much further into. Again, a very well-publicized image from Nankai, which shows very similar relationship between tremor and the depth contours of the subducting oceanic crust there. Perhaps I'll just comment briefly on a conjecture that is not mine, not ours, but that of Steve Kirby, Kellen Wang, and Tom Broker. They noticed that 20 million years ago, California was actually part of what I'll refer to here as Greater Cascadia, the Cascadia subduction zone, before the Mendocino Triple Junction migrated past and assumed its present position offshore northern California. And they noted that with reasonable assumptions that the current trace of the San Andreas Fault overlay the position of a former serpentinized forearc mental wedge. And they speculated as to whether there might be some relationship between these two. I was told by Steve this morning that he has yet to publish this, but I would like to encourage him to do so. I know that Kellen worked up some of these models, and under reasonable assumptions, they can get a serpentinized forearc mantle wedge to exist for timescales of the order of tens of millions of years, which prompts speculation into the role of a gradually dewatering serpentinized forearc mantle wedge that expels fluids into the overriding crust, allows for zones of weakness to develop, and the eventual San Andreas Fault I mean, it's long been noted that the fault is weak and that there are the so-called heat flow paradox and so on. So this provides one with a means for reconciling those observations. So in the interest of staying on time, I think I'm going to finish the presentation with a final acknowledgement. And that acknowledgement goes to the organizations which do us such a great service in terms of supplying high-quality seismological data. In my particular case, Polaris, the Canadian National Seismograph Network, and of course the tremendous efforts of the IRIS EarthScope organization. In fact, I would venture to say that they have done a remarkable job in responding to the plea of Bino Gutenberg in the final sentences of his manuscript, Physics of the Earth's Interior, where he states that in order to make further progress on Earth's structure and on understanding Earth's structure and evolution, it requires that the data must be greatly amplified and strengthened. Thanks very much. I really can't see people very well, so perhaps if there are questions, Peter can...
How shallow does the low velocity zone extend, and does it extend into the region that is seismogenic?
In Vancouver Island, it just reaches that zone. I guess one of the future challenges will be to try to exploit the upcoming OBS observations to map this feature closer to the trench. A lot of questions, I think, will be answered if we can accurately and with we can confidently map the feature, the low velocity zone, into still shallower levels. Okay, I'm not sure I understand the question. You're asking why is the lower crust slower than the upper crust? So are you referring to this diagram? Oh, above the continent. In this region, we have low velocity continental crust juxtaposed against high velocity mantle. In this region here, and so I think that's a logical consequence of the elastic properties of those two lithologies. This is the base of the crust right here. These regions here, we have to be a little careful about interpreting. There is crosstalk between different scattering modes, so one has to be attentive to that when one interprets these images. If these are the features that you're referring to, we haven't interpreted those features.
Can you hear me, Mike?
Yes, I can't see you, but I can hear you.
I'm here. You get a very high Poisson's ratio of 0.4, and you say that there is a decrease in velocity, both VP and VS, in the crust due to high pressure, overpressure. Could you tell us what is the number, what velocity we should get for that Poisson's ratio for the crust? Because 40% is a very large number.
Right. So the question is what sort of velocity reduction does one expect to see associated with Poisson's ratio values of as high as 0.4? And if they're due to poor fluid pressures, then Christensen's measurements suggest velocity reductions of up to 20% for P waves and 30% for S waves. And I would argue that these velocity reductions have led to some of the confusion about where precisely the plate boundary is in Cascadia, because in the past, one of the lines of evidence which suggested a deeper plate boundary came from associations between the oceanic moho and an isovelocity contour of, say, 7.9 kilometers per second. And if we have a 20 or 30% reduction in velocity, of course, the oceanic moho could correspond to a significantly lower velocity. You can do the math.
Can I come back on second question to that? In the calculation which Nick did, he used the word basalt. The oceanic crust consists of basaltic magma, but only small portion is basalt, rest is gabbro.
Right.
So they have a different porosity and lithology, which will not be the same as basalt, which is used for typical calculation, which Nick might have done.
Yeah, that's true, certainly. I think, but the important thing here is that the mechanism allows us to entertain those values of Poisson's ratio. I mean, Nick has performed these measurements on a variety of different rock types. Basalt is about as close as one gets to the composition of the actual downgoing oceanic crust. So I think it's more of a I think it's proof of concept as much as anything else. And I think that in coming years, I know that he's gearing up to perform experiments that will more accurately reflect the actual materials that are involved.